Last Monday, we talked about the attention mechanism. So you can see that we moved progressively from talking about sequence models, which are models that are used to uh, learn information that has historical, a historical component, sequential information. Of course, one of the most important of them is language. As you are speaking, what you are saying is coming in a sequence, and the sequence of words matter, you know. So if the order of the words changes, then it's possible that the meaning may change. So meaning actually depends on the sequence. So we learned that, and we learned how we could just do a single sequence, right? And use that one to maybe have what we call hidden um, the hidden um, value or the context vector, right? The hidden meaning, essentially, basically, of that sequence or of each sequence. Then we now moved from just a single um, network or a single network that can predict, do prediction or classification based on a particular sequence to having a network that can generate another sequence, right? And that's what led us to the sequence models. Then we also talked about the challenge of the sequence model, where you have one sequence that gives you the hidden, um, you know, um, meaning or the hidden value, or what we now call the context vector, the hidden context. And then that hidden context is what is used to generate another sequence, which will be the output sequence, the decoder. And we saw that that was a problem because taking a long sequence and compacting it into a small context vector, you would lose some information there. So the solution to that was to not use the context vector or the hidden, latent meaning of the sequence, but directly allow the decoder that is generating a new sequence to see the input that is coming into the encoder. And we gave it a mechanism that allows it not just to see it, but to determine which of those tokens that come in affect its own output that is generated. That mechanism is what we call the attention mechanism. And then we also talked about the fact that the attention mechanism basically is, think of it simply as a way to map input tokens, right, to output tokens. Basically, to map the importance of each token in an input sequence. How important is it to the meaning, the overall meaning, but not just the overall meaning, but to meaning of each token in the output sequence. And we saw that the attention, there's a whole lot of mathematics around it, but attention basically tells you that for every token that comes into the input, if you are also generating an output, right, there is a kind of importance factor, importance matrix, right, that determines how each word in the input affects the output. That's attention. Then we talked about self-attention, where you're now taking the inputs or whatever sequence it is, and you also do against itself. That's why it's called self-attention. So this sequence here against itself, how each word impacts the effect or the meaning of another word in the same sentence. That's self-attention. Basically, we arrived at the fact that um, based on these different words will have different impact. And ultimately, the entire meaning of that sentence, right, or that sequence generally depends on, the interaction of those words. Yeah, there's a whole lot of maths there, right, where you calculate the attention matrix using a dot, a matrix dot product. between the Q, which is a query vector or the query matrix, and then the K. No, the query vector actually, but then it's a matrix in a sense because it is two-dimensional. The first dimension is the dimension of the query, and then the second is the depth of the embedding, right, which we call D. So that's why we are seeing it as N times D, N by D, right? So you now have the Q, right? The Q gives you the query, and that query is gotten by applying a weight, against the input. The K gives you the keys. That is also obtained by multiply another weight by the input. Then the V is the values, which is also obtained by another weight, multiply. So whenever I say multiply, it's a matrix multiplication against X. And then this Q, K, V now interact with each other. You do a dot product of the Q and K, transpose of the K, and then you scale it because you don't want to have the thing blowing out of proportion. Essentially, it's similar to the exploding gradients we're talking about. So you will scale it by the square root of the depth of the embedding, right? And then we take the softmax. So softmax, remember, is an activation function that ensures that the sum of all of the components of that softmax will be will be 1. So that's the softmax. So what that means is that think of it as a probability factor that you now apply to V. So what softmax does effectively is that it makes all your inputs to be a kind of probability distribution, something like this, right? But when you sum each of the elements, right, you will have the total sum of each of these values on this horizontal axis. The total sum is always 1. So when you now take this softmaxed QK transpose divided by square root of DK, right? This whole thing, right? You now take this whole thing, which we call the attention weights. We will now multiply it by V, which is the actual, you could say the actual value of each of the tokens that is coming in. So that will now give you a distribution that ultimately you are going to now pick, which ones are the most important in determining the meaning of the entire sequence, but also the impact of each of the sequence, each of the elements or the tokens in the sequence on the sequence. So attention is quite, it's not a very straightforward concept to understand. There's a video I'm going to share that will also help. But it's something that over time you keep thinking about it, you will eventually understand it. So we have the attention mechanism, right? This is how you can calculate it. We are going to go into PyTorch at the end of this class and look at some of the things you can do with them. Then we also talked about the masked self-attention, which is what you use typically in a decoder. Because for a decoder, you don't want to give it the idea of the things it is supposed to predict or generate. A decoder is supposed to generate tokens. So when you are, doing inference for decoder, you don't typically give it the future tokens. You only give it the current token that is trying to generate. So this whole masked self-attention mask the future tokens out, right? And I try to explain how that ends up being a triangular matrix. So it masks out the future tokens so that you don't give the decoder an expo or a cheat for it to know what is coming. Rather, it should generate it. Okay, so we also have examples here. And then we talked about multi-head attention, which is basically instead of just having a single head, right? All of these things we are talking about is a single attention matrix, which is the correlation between the sequence and itself, right? Or sequence and another sequence. In the context of transformers, we really talk more about self-attention, which is the correlation between the tokens in a sequence and on each other and on themselves. But you could have multiple of such correlations. So that gives you a multi-dimensional kind of way of looking at the relationships. So one could be like syntax relationships, the other could be semantics, the other could be positional. So that's what the multi-head attention allows you to do. And you can do this very easily with code because PyTorch has written all of this code in a single class that we can use. So we don't need to rewrite the code by ourselves, right? And this is really what's going on inside a multi-head attention, but we won't go into the details. So all of that laid the foundation for the next in this whole historical development of neural network architectures. We now arrive at transformers. So transformer, what is a transformer? Transformer is another new architecture of neural networks. We started off with fully connected networks. Then we talked about convolutional neural networks. That's the CNN. Then we talked about the recurrent neural networks, which is the RNN, the sequence, networks, the LSTM, GRU, RNN. Okay. And then from sequence network, we went to, okay, we can stack two sequence networks together, one as an encoder, the other as a decoder. But then a transformer just totally changed everything. But the interesting thing is that the transformer was based on the idea of attention. So there is a paper that a group of researchers working for Google, after I did a lot of research, they came up with this paper, and the title of the paper is Attention is All You Need, right? And the background behind that title was that before this paper was released, people used to put attention in the middle of encoder, decoder, LSTM. So, for example, if I want to do an architecture, I'll do an encoder, right? So I'll do an encoder. And then, after the problem of, context, uh, the context vector that was too small was solved by inventing the transformer, the attention mechanism, right? The attention mechanism was, like I said earlier, a way to say, okay, decoder can directly connect to encoder and learn, the sequence, right? Or get the sequence directly. So we now had the attention mechanism. So instead of just directly and effectively, this encoder decoder were actually LSTM. So or GRUs, basically sequence models, right? So you have an LSTM or maybe a GRU as the encoder or RNN, any of those sequence models that forms your, encoder. Okay. Let me take this out. So encoder is LSTM GRU, right? Decoder is also LSTM GRU. And then you now use the attention mechanism essentially to connect the two. That's how architectures were before this paper. Between the time of this newly discovered attention mechanism, we're still using LSTMs. And then the LSTMs we were using were basically, okay, we will now use attention, we use an attention matrix basically to connect the two. And that's what was happening. So you have this goes into attention, and then it goes into basically you have the attention matrix where you have the input sequence coming here from the encoder, and then the decoder's own sequence that the decoder is trying to generate, right? And then you have the attention matrix, which I have already shown. You can think of it as a table that maps a sequence against itself. But in this case, what was happening is they were not mapping sequence against themselves. They were mapping the encoder sequence against the decoder sequence, what the decoder is generating. So yes, the architecture was like that. Encoder, attention, decoder. But the encoder was an LSTM. So LSTM, attention, LSTM, or GRU, attention, GRU. And the attention, remember, is just a matrix, just a matrix multiplication, a dot product, right? That whole dot product scaling, softmax, and then you multiply that again by the V. That was attention. So attention was a faster mathematical computation to do than the LSTM and GRUs. So what this Google team of researchers found was that we could actually still achieve almost the same level of performance without needing the LSTMs at all. Basically, what they came up was, we don't need this, we don't need this. We can even replace the encoder with a simple, fully connected network and the decoder with another fully connected network, right? In fact, you don't even need LSTMs at all. Essentially, what they were saying is that you only need attention. You only need the attention matrix, right? To be able to still achieve encoder decoder capabilities. That's why that is the essence of this name when it says attention is all you need. Attention is all you need. You don't need LSTM anymore. You don't need GRUs anymore. You don't need sequence models. So they came up with a mechanism that removed the recurrence, the recurrent neural networks, and the convolution, because some architectures even use convolutions on top of the recurrence, and said we can achieve the same level of performance, right, just by using attention only, just by using that attention mechanism only. And that's how they came up with that attention is all you need. So the transformer became the new architecture. And we're going to talk about architecture. The transformer architecture basically only uses the attention mechanism, right? Along with the fully connected networks. So why was the transformer such a big impact, a big difference? Because first of all, recurrent neural network training is sequential. You can't parallelize it. Remember, it has to do with sequential information, right? And we are talking about natural language processing here, not sequential data like time series data. We're talking about more like just language, basically. This was all really in the domain of NLP, natural language processing, right? So in the domain of language, sentences, paragraphs, yes, it is still sequential, but the problem is that if you want to train a a sequential model, you have to pass the input sequentially through that model. Remember, you're not that unrolling that we always see is just a virtual thing. It's not real. Reality is just a single layer. But that single layer will have to pass that sequence one at a time, one at a time, one at a time. So there was no way to parallelize that operation and put it maybe, for example, in a GPU where you could compute each time step in parallel simultaneously. That would have sped things up. That was a key limitation with the recurrent neural networks, whether it's RNN, whether it's LSTM, whether it's GRU, and all the other variants. But with transformers, remember, attention is just a dot product of matrices, right? Then the only thing you need to do is how to obtain those matrices, which you use the QKV projections to achieve those matrices. The QKV projections are essentially fully connected, um, you know, um, feed-forward networks, right? But the interesting thing with transformer is that you could take all the entire sequence and feed it all in parallel because the inputs were no more sequential inputs. The inputs were all parallel. Remember at the beginning when we were talking about fully connected versus sequential, we're saying one of the problems with fully connected was that it does not have any idea of sequential or time or historical sequence of data, right? That was the advantage of the sequence model. But now that disadvantage becomes an advantage because you can now take all the data and put it in parallel. Because these guys prove that what you really need in natural language is not really the sequential nature of the data itself, but rather the attention, the effect that each token or each word in a sentence has in on other words, whether words that came before it or words after. So essentially, they replaced that idea of sequentiality with the idea of attention. And so with that, it was possible to remove the main sequential aspect of this model, right? The attention came in and replaced the sequential models, the recurrent neural networks, LSTM, and so on. And so we now have transformers that are fully parallel, right? So you can plug in multiple, uh, data sets. You can even, in a single sequence, you can essentially process all the tokens in a sequence all at the same time. And that works very well with GPUs because GPUs are really good at parallelizing workloads. GPUs are very good at doing small computations all at the same time on multiple data. It's what they call single instruction, multiple data, right? You give, uh, let's say you wanted to do a matrix multiplication, a matrix that is 100 by 100. That's maybe 10,000 numbers in there, right? With a GPU, you don't have to do each of those calculations one at a time. You do all 10,000 at once, right? So it takes 1/10,000 of the time because GPU is designed for that kind of high level of parallelism. So that was the beauty of this. The other beauty of transformer is the long range dependencies of long sentences, of long paragraphs. The main limitation that RNNs and GRU and LSTM had was the vanishing uh, uh, you know, vanishing gradients problem, right? Or vanishing weights. So even when it is solved with the LSTM and the GRU, right, you still have a little bit of it, even though LSTM did very well to solve that. But transformers turned out to be really good with long dependencies. So with transformers, you could actually have entire long pages that the relationships between a word at the beginning of a page and another word at the end of the page is still fresh and strong, right? And that is what enabled these foundation models, what we call foundation models, which we're going to talk about in a bit. Some of the foundation models that we also, talked about, we talked about a lot of them. Talked about foundation models. We'll talk about GPT, which is a decoder-based model. We talked about BERT, which is an encoder-based model, T5, Llama, and all of this. This all use this transform architecture. So in today's world, the large language models that we are hearing of today, the GPTs, the chat GPTs, and all of that, all use the transformer architecture. So this is how the transformer architecture looks like. Um, at the high level, this was the original design by the team of Google researchers who wrote this paper. So this drawing kind of is stamped, etched in history. You see this drawing in a lot of places, right? Let me break down this drawing. It is made up of two sections. The first section is the encoder. So interesting enough, you say, okay, I thought we had removed encoder and decoder when we say attention is all you need. So why are we still talking about encoder and decoder again? But you will now see that the difference here is that the encoder that we have here doesn't have any sequence models in it. It doesn't have any LSTM or anything. The decoder also, likewise, doesn't have any sequence models. These encoder and decoder are just standard multi-layer perceptrons, basically um, feed-forward networks that don't have any recurrence in them, right? Maybe fully connected networks. So we're going to look at that. But it's made up of two sections, right? The encoder section and the decoder section. So typically, the two main blocks are the encoder and the decoder. So you pass an input into a transformer. The transformer does encoding, right? And then it passes the output of the encoder to the decoder, right? So remember, the encoder is the one that takes a sequence and generates a single meaning. We called it context vector before, but now it's more than a context vector, but you can call it an attention, weights, right? It gives a meaning. Then you can take that meaning, but the beauty is that with the decoder, not only are you taking the meaning, you are taking the entire sequence as well. And we're going to see it here. So you take that into the decoder, and the decoder is now able to generate its own sequence, right? Remember what we said about encoder-decoder architectures. Before we're talking about sequence to sequence models, right? Where the sequence model, you have one sequence model as the encoder, and you have another sequence model as a decoder. But now you have encoder-decoder, and none of them is a sequence model, right? Then in between, you have the attention mechanism, or inside the encoder, you have an attention mechanism, and inside the decoder, you have another self-attention mechanism. So that's the simple architecture of a transformer. The encoder, its own job is to understand the context of the sequence and to build the semantic representation, essentially to build the meaning of what it is receiving, right? The sequence, right? The decoder's job is to generate a new sequence based on that meaning, right? And as it is generating it's a new sequence, it will attend to the encoder output. So what attend in this case means is attention, is the attend of attention. It will essentially determine which of these elements or tokens in the encoder output matter to what it is generating. Then it will maintain causal masking. So this causal masking is what I mentioned before, where you will not want, as the encoder's output is coming in, you don't want to allow the decoder to see the things that are in the future, right? That it's supposed to generate. So use masking. We've already talked about that. So effectively, the responsibility is shared between encoder and decoder. The encoder's responsibility is comprehension or understanding of the sequence, while the decoder is to generate a new sequence based on that understanding and based on the instruction. So, for example, it could be, or based on the training, let me not say instruction, based on the training or the purpose. The purpose could be generate a summary, right? Or the purpose could be generate this same sequence in another language, right? Or it could be use another medium or something, right? So we will go into the breakdown of this encoder and decoder separately, but just take note of this drawing. You have the input, you have what we call an input embedding. We have a positional encoding. Then we have the two main elements of each encoder or decoder layer. You have the attention layer and the feed forward layer, right? And so we'll talk about that in the next slide. So the encoder block, right, is made up of these 1, 2, 3, 4 blocks, right? If you don't count the input. But you have the input. The input is the sequence that you want it to learn, how to handle. Now, this input is passed through 3 projections. So remember, we already mentioned this. You have the Q projection, the K projection, the V projection. And we're using dense layers. Dense layer is effectively a fully connected layer. And if you remember where I had mentioned this before, each of these is given a weight. The dense layer actually have weights, right? That's what we are talking about. So, for example, you have WQ, which is the weight for the Q, um, layer. That's basically the weight vector here, right? So the dense, when you train this dense layer, is basically the weight that it learns is trained. That's the WQ, right? Which you will apply to the input. You apply it to the input, and let me just use so you apply it to the input and you will get the Q projection. So the Q projection, like we said, is Q is the query. The query is basically what the decoder uses to know, okay, what am I looking for? Okay, what am I looking for? The key is what the decoder will say, okay, what is the encoder giving to me? What are the possibilities, that the encoder is giving to me? That's the key. And it also has its own weights that projects the input into that. And then the V is what are the actual values when I have eventually calculated between WQ and WK, which um, of the tokens really matter most, right? What is the actual value that will then be applied to that weight? So effectively, you're using WK and WQ, you're using Q and K to calculate the weight of how much the V's will pass through. So this is the architecture, right? And the architecture has been proven to be very powerful. And of course, that's what gives us all of the magic that we're seeing today with large language models, the GPTs, and all of that, right? This architecture you're seeing here. So you have input, you have the three weights, the three dense layers. The three dense layers will now have outputs, the Q and the K. The Q and the K will just do the matrix multiplication, which, like I have mentioned before, the matrix multiplication is Q and times K transpose. So this transpose is actually um, um, let me just use transpose as so that we know, right? So we are essentially taking Q times K transpose. That is the matrix multiplication that's going on here, right? Then the output is a scale. So remember the scale where we take this Q times K transpose, we scale it, we divide it by the embedding depth. So this is now QK divided by the square root of DK, right? This is what we've seen this already. That is the scaling phase. So the scaling phase is you take this QK transpose that comes from the matrix multiplication and you scale it, you divide it by the square root of DK, and then you do the softmax. So this softmax, like I said, the softmax, the QK divided by square root of DK gives you what we call the attention score. And then the softmax will now normalize this attention score so that the sum of all of them will add up to 1. So that means that effectively you get a probability distribution, right? So you end up with something like softmax, right? I think we've seen it before. So softmax of you know Q K transpose divided by square root of DK, right? And that is the attention weight. Then we take this attention weight and we multiply it by the V vector. So effectively, what you're seeing here is just the schematic representation of the same thing we have seen before, right? Is a schematic representation of this same attention formula where we had, this is the attention formula, right? this attention from some softmax of QK transpose divided by square root of DK times V. That is what this is, basically. That is what this is. So Q times K transpose divided by square root of DK, right? Softmax it and multiplied by V. And so a single attention block does that calculation. Then the next is the add and norm. So the add and norm is going to add this, what we call a skip connection. So if you remember when we were talking about convolutional neural networks, we said you can add a skip connection, which is take a little bit of the input and still add it to this attention value, the attention scaled projection of the value, right? Attention scaled projection of the value is what is coming out here. Add a little bit of the input, and then you do what we call layer normalization. So layer normalization is just normalization. We talked about normalization already and standardization. So that's just a way to scale the values down so that they don't blow up, right? It's to scale the values down into a range. But in layer normalization, unlike, there are different kinds of normalization. There's what we call batch normalization, which is you normalize all the values in a particular batch, right? But layer normalization is you normalize all the values in that particular layer, right? In that particular layer, not across the entire, um, you know, data batch. So that's layer normalization. So it's just normalization, but the subset of data that you use for the normalization is what makes them call it layer normalization. So you now see that the encoder is made up of the attention, which is this number one, that's a multi-head self-attention. Then you add that to the input, then you do the layer normalization. Then the output from this layer normalization, you pass it through a feed-forward network. So a feed-forward network is, we'll see in more details about it, but it's just two layers of you know, fully connected networks, right? The main purpose, always remember that when you put in a feed-forward network, you are bringing it in to kind of um you know, that's where the meaning or the representation, the knowledge representation is kept or is stored or is learned in the weights, right? Just like when we're talking about convolutional neural networks, and we say that all of these conv2Ds that we stacked up, they all do feature engineering basically, but the last few layers of fully connected feed-forward network now extracts or represents the knowledge or the meaning in that layer. That's the same thing here, basically. The attention layer is acting as a feature extraction. But this time around, it's not just features, but the interrelationships between the tokens and the elements in the sequence. That's what attention does, right? So it still is another form of feature engineering at the end of the day, right? And then the feed-forward network will now, you know, extract that the knowledge representation is in the feed-forward network. And then from this feed-forward network, you still have another addition and normalization. So you're going to still take the output from this, right, and add to what the feed-forward, comes up with. And that addition, you still do another layer normalization. So in a transformer encoder block, you have two-layer norms going on, right? The first one immediately after the self-attention, or it could be multi-head attention, but self-attention, right? And then you have the normalization after a feed forward. That's the output. So you can see the benefit of the skip connection again is to minimize vanishing gradients. So you can have deep networks, right? It turns it from a multiplication of weights to an addition. So this adds an addition component. And that's it, right? The residual connections prevent vanishing gradients. So they allow very deep models. So basically the output is going to be what each layer does, right? Plus the original output. So What this does is that it still allows a piece or an element of the input to still find its way and propagate across all the way to the output, even though it gets modified by what is going on in each of the layers. That is the encoder block. So we now have the second, which is the decoder block. The decoder block is more or less exactly the same thing as an encoder block, but there are a few small differences. The decoder block takes the inputs, right, that you are training the model on as well, right? And then, but instead of having a standard self-attention, it has a masked self-attention, right? And the only difference between a masked self-attention and a standard self-attention is that a mask, that upper triangular mask I talked about, is applied here to the attention matrix before the softmax, right? Or yeah, before the softmax. There's a way it is applied so that by the time you do the softmax, right, the upper triangular values of the attention matrix will be zeroed out. That way, the future predictions are zeroed out. So you don't end up giving the, the feed forward future values. It doesn't see those ones. So that's the only difference. We will introduce this mask, and this is the mask, like I mentioned before. This is the upper triangular mask, right? You can see that the upper triangular half of this is zeroed out. So while the lower is still ones. So what that means effectively is that the attention matrix itself, when you multiply this kind of mask on it, right, the upper triangular side of the attention matrix will become zero, while the lower triangular will maintain its value. That's just what the mask self-attention does. Apart from that, everything else is the same. So you will see it here. The input is the same. You still have the three WQ, WK, WV, still the same three projections. You still have the MATMO, right? The Q dot K transpose, which is a matrix multiplication. You still have the scaling by square root of DK. But after the scaling, before you go to softmax, you have the mask. This is the upper triangular mask, right? That will remove the future um, uh, aspect of the attention matrix, which is actually what you want the decoder to generate. So if you give it to the decoder, you're effectively um, giving expo. So the decoder is not really generating what it has learned, but what you are giving to it, or what the encoder is giving to it, which would be wrong. That would be biasing the decoder. So that's what the mask does, right? So after that, you still do the normal softmax. That gives you attention weights, and then that softmax, you now apply it against the value and you get the matrix. So that's what you get the uh, the attention matrix, right? This is attention, self-attention with mask. So with this self-attention with mask, we still have the skip connection coming in. And then we have an output. That output here, which is the sum of the um, the input with the mask attention, right? That output is then passed into a cross attention layer. So the main difference between a self-attention layer and the cross-attention layer now is that we are taking the key from the encoder. This is what was happening in the past with sequence-to-sequence models, where we take the key from the encoder, but we'll still take the query from the decoder. So in this case, it's the same thing, right? The key and the value are coming from the encoder, and the query is coming still from this input from the decoder. And that's why we said the query comes from the decoder. The query is what the decoder uses to ask itself, what am I trying to predict? What do I want to predict? While the key and the value, right, comes from the encoder. So when the decoder is trying to predict the next token, the decoder is going to check, is going to ask itself, what am I going to predict? That's what the key, that's what the queries give to it. Then it looks at the keys, what has an encoder, what came into the encoder, right? That is looking at the key. So it's still going to do the Q and K matmul, right? Cross attention is going to do exactly the same thing as self attention. The only difference is that inside the decoder, in the cross attention, there is no masking, or there's no masking here because the masking has already been done above in this layer. So there's no masking. But that's the first thing. Then the second thing is that the Q is coming from the decoder, while the K and the V are coming from the encoder. So it's still going to be the same thing, QK, right? Q dot K transpose, where Q comes from decoder, comes from encoder. You do the math mode, the dot product. You do the scale divided by DK, right? Then you pass through the mask, but in this case, you're not going to mask it. Then you just move on to softmax, right? Which basically normalizes all the values to sum up to the outputs to sum up to 1. Then you take those weights and you apply to the V. The V is still coming from the encoder, right? And then the output comes out from here. So you now see that the output from cross attention, we will still have another skip connection, right? That will then be added to the output from cross attention and then normalized again the same way, right? Normalized again to reduce the values to a smaller range, right? That's what normalization, standardization does. So this is again layer normalization. Then the output from here is taken into a feed forward. So we'll look at feed forward next. Feed forward, remember, is what now does the knowledge representation. So with mask attention and cross attention, the decoder is able to get some information from the encoder, right? That helps it to decide what should be the next word. So you can see that it actually learns to predict the next token based on the input it gets, what it has already predicted, plus what is coming in um, from the encoder, right? And then the feedforward gives you the knowledge representation, essentially pulling all of those features together and saying, okay, this is what it means. This is what should come out, right? And there is still another skip connection. So you can see there are actually 3 skip connections. So it keeps connections, ensure that a little piece of the original input still finds its way to the output to avoid vanishing gradients. So what this decoder does is it basically it allows the decoder to check and ask which input tokens are relevant right now. It takes its own input, right? Forms the query. Which one matters? What do I want to predict next? And it compares it with what it gets from the encoder. So of course, we talked about the feed-forward network, which is this feed-forward. We've seen 2 of them here and here. So this is a feed-forward network. It's just basically 2 dense layers stacked one on top of the other, right? Basically a fully connected layer on top of another fully connected layer. But there's something very special about this. The special thing is that the number of outputs from the first layer is always much, much larger than the number of inputs, right? So what that does is that it helps um, to essentially increase the amount of knowledge that can be represented by this. But after this, it is squeezed back to exactly the same dimension as the input again, right? So what it does is that it helps the model to have a deeper understanding of the tokens. So the reason why you expand the dimension is to create representational richness, to create representational richness. So the attention mixes the tokens, right? That's the attention block, both the encoder and the decoder, and gives you an idea of the relative importance of tokens to each other and to the overall meaning. But the FFN, the feed-forward network, does gives the model a richer, deeper understanding of the tokens, right? So interestingly enough, of course, FFN has a much larger fraction of parameters because it is fully connected with, and you can see that the middle um, dimension, the size is really large. This is a summary of it. This is basically a stacking of two layers. Um, effectively, um, this is a ReLU, by the way, but there are other kinds of activation functions that are used in between, in this output here. We could use ReLU, we could use SWIGLU. There are so many different ones, which I think I shared a video of different activation functions. So that's it, right? Now, the one problem, which if you were thinking along with me when we were discussing this whole switch from a recurrent encoder decoder to a transformer encoder decoder, one thing you find is that, okay, we've lost the idea of the sequence or sequentiality because we have gone back to using feed-forward networks, right? We've gone back to using fully connected networks. So that means that attention doesn't know anything about sequence. Attention only knows how each word, or each element of a sequence attends to the others, right? So it can give you that. But if you actually take this, the dog chase the car, the car chase the dog, you find that they will look identical because it's still that same problem is still there. There's no knowledge about sequentialness. So how do we solve this problem now with this new attention architecture? We cannot go back to sequence because it will be slower. We've already established that attention is massively faster because you can massively parallelize the computations. So the solution was to come up with what we call positional signals or positional encoding. So what that means effectively is that if you have a sequence like this, the dog chased the cat, you will tag each position with a unique number, right? So you could, for example, tag this position with number 1, tag this position with number 2, right? Number 3, number 4, number 5, right? So the token will be enhanced by this positional tag, right? So for example, if we now extract this out, this will now be the word, the token actually changes. That's what positional encoding does. It slightly changes the token by adding these tags to it. So this will now be the 1, right? Dog 2, right? Chased 3, the 4, cat 5. It's something like that, right? So if we now if we swap the words, right? This one will now be the 1, cat 2, right? Chased 3, the 4, dog 5. So in a way, it has now disambiguated that this dog here in position 2, its meaning has slightly changed. The positional encoding has basically slightly changed the meaning so that this is slightly a different meaning from the other one because now we are now including the positional information. So this will not now be identical because these are not identical anymore. This is dog 2. This is dog in position 2 versus this one that is dog in position 5. So even when you jumble it up and put it back in, right? Even if you were to jumble it back up and it will now be the cat 5, chase 3, the 4, dog 2, right? That kind of is different. So the way that the transformer will interpret it or the meaning it will assign to this will be different, right? From the meaning it will assign to this simply because of that. And that's really what positional encoding does. So the original transformer paper used what we call sinusoidal encoding. That's the encoding. Here I used a linear kind of because the numbers are increasing linearly 1, 2, 3, 4, 5. But so the problem with the linear encoding is that the number continues to rise, unlimited without limit, and will basically you can if the sequence length gets to maybe like 10,000, that means the positional numbers will also increase to 10,000. So that sometimes may be difficult to manage, right? So the original paper did not use that kind of linear thing. Rather, it used a sinusoid. So a sinusoid is effectively using like a sine wave. Okay, so you use the values following a sine wave or a cosine wave. So if that was the case, this could be something like maybe zero. Let me assume I'm just using 0 pi over 2, right? Um, which is like this will be pi over 2, right? Oh, sorry, that those are the angular positions, not the actual values. But it will be maybe something like 0.5, right? Then it will get to 1. Then on the way down, it goes back to 0.5 and it goes back to 0. Or maybe even not doing a full cycle of the sinusoid, but more like 0, 0.1, 0.3, you know, 0.5 or something like that. So it basically uses the numbers. I guess the benefit of using sinusoid is that it never goes above 1, right? But sometimes it can get down to 0 and it can also get down to -1. So that's what they use. But there are so many different other ways of disambiguating um, the sequences based on their position using this position encoding. So yeah, so this is the basically a position encoding, right? We use sine of the position divided by 1,000 or 10,000 raised to the power 2i over d, right? So this allows you to spread it over a long, thing, right? Um, and they do sine cosine interchanging. So all the even numbers for I, in any range, 2i will mean an even number. So all the even numbers will use a sine, right? Position, the sine of the position divided by this, while all the odd numbers, odd position tokens rather, would use the cosine, which is position. So it gives a kind of interesting um, pattern, right? The sine cos gives very unique patterns. The other beauty of using sine and cosine is that you can have infinite extrapolation. Because remember, like I said, if you're using linear, you could have a situation where the position encoding can become so large, right? And if we are using a fixed number size, that will result in number overflows that could be problematic. But with sine, cosine, right? It just goes infinitely. The numbers will always switch between 0, get to 1 at the highest and -1 at the lowest. And it also encodes relative distance because in a way, when you get to the point where it gets to the top and starts going down, it is like saying, okay, we have started again. When it gets to 0, if after a full cycle, it is like, okay, we have started another cycle. And that's the whole idea of relative distance. So for positional encoding, right, in most cases, you just add it, right? Essentially, I'm seeing add here, but typically positional encoding, you concatenate, you append it to the end of the embedding so that it kind of extends the embedding a little bit. But yeah, I've also seen addition, right? So we're going to see that as well. Because when you say add, it means the position is not part of the token representation. But if you want it to be part of token representation, like I showed you, I appended one at the end, it's going to concatenate it. So this function here basically does this formula, right, in code. So position divided by 10,000, right? Which is basically this position divided 10,000 raised to power 1 over D model. So D model is a depth, like that's a decay we were talking about, the depth of the embedding, right? That's D model. So so we can now check if it is you calculate the angle. So for position I, you use the sine. For position I plus 1, right? We use the cosine. And that will basically include all of the tokens, right, based on their position in the sequence. Okay, so with that, we can actually do a very simple transformer. You do a transformer encoder layers. So remember, the encoder is made up of multiple layers. We just looked at one layer. This whole thing here is just a single encoder block, a single encoder layer. So if you want to train most models will have hundreds of layers, right? Hundreds of layers. So if you want to actually train a proper transformer, you would use a lot of layers. Okay. So when you are writing the code for it, you first of all define one single layer, right? And in this case, for example, we define this layer to be a transformer encoder layer. The D model, which is the depth, the embedding depth, is 512. N is the number of heads for a multi-head attention. Then the feed forward, this dimension of feed forward. So remember we said that the feed forward layer, this FFN, this in between has a different size, right? So 2048 is picked here. So essentially this model matches what I drew here. 5112 is the D model, which is the standard embedding depth. But we now do a FFN dimension of 2048. And that's what you have here. Then batch first as usual. So when we define a single transformer encoder, then we now create the entire, sorry, a single transformer encoder layer. Then we now define the entire encoder stack by specifying the number of layers, right? We use a transformer encoder, specify the architecture is single layer that we have configured, and then the number of layers, right? And then with that, we can just run inference on it. So with this just is a simple way of building an encoder. And the interesting thing is that the BET, the very first Google transformer, was actually built as an encoder. It wasn't an encoder decoder stack. It was just a single encoder, right? Then there are other improvements which we'll talk about. Rotary positional embedding rope. So this is just a better way, right? Just a better way for you to do positional encoding or positional embedding. Instead of using that sine wave or sinusoidal one that I just showed you, right? Rope tries to do something more fancy, trying to maybe essentially rotating the vectors in embedding space, and then it encodes the relative position of the vector. So rope is just another way of doing positional encoding or positional embedding, right? It's used in GPT Neo X, it's used in Llama, it's used in Mistral, right? It's better because it has stronger long context performance, smooth extrapolation, and better attention decay. So there are a lot of these different small elements that you would typically introduce into your model, right? To make your model better. Okay. So that's rope. Then there are other things. I'm not going to go into all of this, but there's a whole bunch of other improvements that came later on, right? We have what we call a multi-query, and you have the grouped query. So multi-query is where you now have multiple queries, right? Because multi-head attention is memory expensive. Each head will store a separate key and value matrices, so it takes a lot of memory. So if you want to improve a little bit, people have tried to improve this. So one way is the multi-query attention, where instead of having separate key and value matrices, you have many heads that will share one key and one value matrix. So you get faster inference, you get lower memory usage or consumption, and it's ideal for LLMs in production. So you see some of these LLMs use that one, the Palm and the Falcon. Then you also have the grouped query attention. So this one is kind of middle ground between having a multi-head attention and a multi-query, right? So it balances quality and speed, right? So That one is using Llama 2 and Mistral. So there's been a lot of research going on in all of this. These are more advanced architectural improvements that people have done on transform architecture for their various large language models, right? So we're not really going to go into all the details, but it's just good to know that these things exist. Then there's also what we call flash attention. Flash attention is basically a way to improve on the calculation speed or the calculation attention. So of course, one of the things you find is that if you are building models, especially if you are doing it um, from scratch, or you are trying to fine tune or tweak implementation, like a few things I have done in the past, you always find that the attention block is the most expensive part of computation. It's the one that takes the highest amount of time and computation. And the reason for that is because your attention block is actually made up of a matrix that is made up of the full maximum sequence length times the maximum sequence length, right? So for your information, let's assume that you have an input, right? And your input is typically like, let me use this. It's typically in this is this manner. B is the batch size, right? So it could be 64, 32, whatever. Then you have the sequence length, right? And then you have the embedding depth. Let me just call it, yeah, embedding size or embedding depth. We'll look into that when we start talking about this, because normally before you pass a sequence in, right, you have to do embedding, right? You have to do embeddings on it. These are words. The meaning of words can only be represented by embeddings. The vector embedding, right? Which we had looked at earlier on. So, um, so if you have a sentence that has several words in it, like um, the quick brown fox, right? Or the cow jumped over the moon. Let me just use that. The cow jumped over the moon, right? Now, the typical thing you would normally do if you want to take this sequence and you want to train a model, right? Transformer or even LSTM or GRUs, you need to first of all convert these words, okay, into numbers, like we have mentioned before. All neural networks deal with numbers. So the first thing you would do is to take these words and you would tokenize them. So tokenize them is you would generate tokens. Now, typically the way you generate tokens, you can just split. Let's assume we tokenize them by word. So each word here, right, is considered a single token. So you're going to have 1, 2, 3, 4, 5, 6. In real life, it's not exactly that way, but just for the purpose of understanding. So each word is converted to a token. And typically when you're tokenizing, you tokenize these words and you associate them with a dictionary and their position in a dictionary. But at the end of the day, right, let's forget all of those intermediate steps. The main thing is that each of these words, you now pass it through an embedding that will convert the word to its meaning, the token to its embedding. And remember, embeddings are just vectors, right? Basically, it's vectors. So the word THE might have an embedding that's just a sequence of 0.1 comma, blah, 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 right? Sequence of numbers. That represents THE. Another embedding represents cow. So another sequence of numbers that can start from anything. Remember, the actual numbers don't depend on the sequence or position, right? They depend on what a neural network had learned, right, as its own internal meaning of these words. So this first embedding is for THE. This second embedding is for cow, the word cow. You now have another embedding here, right, for jumped. Then you have another sequence, another embedding here, rather, for over. Then you have another one for the cow jumped over the. So you have another one for the, right? And then you have another one for moon, right? So what you now have is a sequence of embeddings, right? So this sequence of embeddings is going to have a length of sequence length, right? And embedding size. So let's say your embedding size was maybe 128, right? Now, this is a sequence. So sequence will have um, a variable length sequence, but typically, um, what we do is that it may have a variable length sequence, maybe a variable length sequence, but we normalize all sequences and give it a fixed length. So let's assume we say, okay, the highest length or highest sequence, number of words basically, or the number of tokens that I'm ready to deal with, or I want to train my model, I want to do build my model to handle is maybe 2048, right? You'll notice I'm using powers of two here. It's kind of um it's kind of a convention, but it's based on the fact that powers of two are much easier for you to parallelize and optimize in GPUs. So the batch size, this is now each batch. So this batch size does not matter. This is basically something that happens outside of the GPU. So we now have a input of this shape, right? N can be any number, right? Then 2048 is the length of the longest length of input that I have designed this neural network to be able to handle. And then 128 is the embedding depth. Now, this is the input, right? This is the input that we see when we are talking about when we're looking at this um, oh, looking at this and we're saying this input here has this shape N 2048, 128. Now we apply the dense weights and we're going to get QKV, right? Now let's assume that we apply the dense weight and let's assume that the dense weight that we apply is um it's basically what the weight does most of the time is just to change the embedding dimension. That's what we call a projection, right? It's basically going to change the embedding dimension. And sometimes it will either increase it or it will reduce it. It does not affect the sequence at all. The sequence length remains. So when you take this input, you pass it, you are not going to have a QK, QV, and you're going to have a QKV basically of these three, right? So the N is still there, right? I will ignore the N just for the sake of this. Maybe I'll just use a star here so that we don't get over. So our Q will now have a new, let's say I change it and I have D model of 512. So the weight is going to essentially project this 128 into a 512 dimensional space, right? We are still having sequence length of 2048. In other words, the maximum number of words or tokens that my model can consume, ingest, and do inference is 2048 words or 2048 tokens, right? So we now have a Q, and then we have the K as well. The K is also going to be that. Again, I'm going to just replace the batch with a star. Typically, we use a -1 or something. And then we have the V. So we have these three projections. But the thing you have to understand is that the actual values inside the QK and V will be different because the weight matrices that were used to generate them were also different, right? So this is still going to be 512. This 512 is now what we call the D model, which is the embedding depth. So this is now the embedding in attention. Now, the next thing you do is Q dot K transpose. This is where the problem arises. When I do Q dot K transpose, right, I'm effectively transposing this K. So when I do Q dot K transpose, let me show you what is going on. This is Q, right? Star, this is Q, right? And you do a dot product. and then this is K transpose. So K transpose is basically going to be the same as Q, except that you are going to flip these two. So this will be 128, sorry, this will be 256, 512 rather, because we have already projected them into these dimensions, 512 and 2048. Now, when you're doing matrix multiplication like this, the inner dimensions will normally go away when you do a dot product. The inner dimensions go away, right? What I mean by the inner dimension is, let me remove now the batch size. We are only always going to do dot product between the last two dimensions of any sequence or of any tensor rather. So yeah, this has multiple dimensions, whatever, but when you have done transpose, you're transposing the last two dimensions. So we transpose the Q, this is the Q, right? But this is the K. The K has been transposed. So you can see that its dimensions have been swapped, right? And then when we're doing the matrix multiplication, the middle dimension always adds up and disappears and becomes a single dimension. And we'll now end up with this is Q dot K transpose, right? This Q dot K transpose, which is what's happening inside, that's the attention block basically, right? So you're going to end up with a new matrix, which is going to be 2048 by 2048. So this is the matrix. This is the attention score. You cannot, of course, here we can do this divided by square root of dk. We can do the softmax, but that doesn't change these dimensions. So what attention effectively does is that it turns your input that has this shape into a matrix whose dimensions are the sequence length by the sequence length. That is this attention matrix. So that is a 2048 by 2048. The sequence length by the sequence length. So this can blow up. This can blow up massively, right? That's why they say it's an ON squared. ON is a way of measuring what we call complexity, right? O notation, complexity of a computation, right? This is sequence length. That will be the width of the attention. Of course, it makes sense now. Is that not what we're seeing, right? This is sequence length, which is also the height. It makes sense, doesn't it? Because when I was showing you attention matrix in the previous screens, if you go back, you will see I was always doing like where I showed self-attention here. This is the sequence length, right? This is the sequence, and this is the sequence. So the attention matrix is always the dimension is sequence length times sequence length. So what this means is that it actually increases ON squared. That means the size of the matrix is n squared, where n is the sequence length. So as if your sequence increases by times 2, the actual attention matrix increases by times 4. That's n squared. So attention is the heaviest part of a transformer architecture. It is the slowest part, is the one that takes the most compute, and is the one that takes the most memory. Okay. So at some point, memory becomes a bottleneck. So think of some of the current large language models of today, right? That people are building, context. When you hear context window, right, or context size in a large language model, it actually refers to the maximum sequence length that that model has been designed for, right? So when you say, when you see that a model has 1 million is a context window, 1 million tokens. That means it has the inputs into it is 1 million. You can basically dump 1 million parallel tokens into it and it computes. So if it has 1 million parallel tokens coming in, where each token has an embedding depth of whatever the embedding size may be, right? which is a different matter altogether. It could be 512, it could be 1024, right? It could be 768 or whatever, right? Then you will know that means the attention matrix is going to be 1 million times 1 million, which is 1 trillion. That's 10 raised to power 12. That's a lot. So memory becomes a bottleneck for very large, um, you know, neural networks, very large language models. Okay. So the flash attention idea is the idea where you, instead of trying to do this attention all in a single block at a single go, you take the attention and you calculate it in smaller subsections. So I would compute the attention, um, I would basically split this into smaller subsections, and I'll compute the attention for each subsection separately, right? So that means the amount of memory is much less. So for example, the 1000 or 1 million context window, you could split it into maybe 200,000, right? Or even 100,000, or even 10,000, right? And then you compute each of these. And since these are dot products, right, you can actually compute each of them individually and then tile them back on, right? This is one of those really complex GPU operations that GPUs can really handle very well. And the GPU libraries like CUDA and so on, Cutlass, are designed to really handle this kind of complex computing. So anyway, that's what flash attention does. The benefit is, of course, more speed up, right? Because you're effectively, computing less at a time, even though altogether you have to do multiple iterations, right? Massively reduces memory consumption, and it allows long context training. Basically, it can allow your models to have even larger context windows. But note that this is just an algorithmic optimization. The architecture did not change. It's still the same architecture. There are other things too. We have what we call linear attention, where the attention is no more um, an a complex a matrix of sequence length times sequence length, but rather a single linear matrix. So there are a whole bunch of other things that are done just to improve the transformer architecture. So that's it. Transformers are the foundation of the uh, large language models of today. Next week, we are going to come and look at what we can really do with large language models. But I'm going to just show you how you can build a simple transformer architecture. We are going to solve a problem of training a model just in principle, right? An encoder model. By the way, I did not mention a decoder here, right? But a decoder is the same thing. So we'll talk about decoders next week. It's basically the same thing, same principle. Um, so if you look at we can do word prediction. So because we didn't do any hands-on with LSTMs or sequence models, I'm going to show you how we can do word prediction with an LSTM. And then we'll do that same word prediction, but this time around we'll use a transformer, right? So let's start off with simple word prediction with an LSTM. So it's very easy to make an LSTM. Okay. Um, PyTorch has already done it for us. Let's see if I can get it from Drive. Um, so we have word prediction with LSTM. So let's start with this. So remember, LSTM is a sequence model, right? And then we will also look at word prediction with transformer. So the idea of word prediction, like I said just now, is you have to first of all, so first of all, it's always a good idea to use a GPU. So I'm going to change my runtime to a T4 GPU, so it will be faster. Even though for LSTM, it still won't be that much faster because LSTMs are just generally slow, right? Okay, so the first thing is this. Whenever you're doing natural language processing, you have to convert the words into numerical representation. That's what I called embeddings. These embeddings are obtained by, well, in the old days, people used to handcraft embeddings, right? But they were not really good. But the good news is that over time, the system kind of bootstrapped itself. So neural networks, when they started learning and understanding natural language, their internal representation of the words, right, were extracted. And that's what we call embedding. So if you go to Hugging Face, like I think I showed everyone that, you can actually get models. There are a lot of them, even on Open Router. There are models that will give you, you can just call and you can get embeddings. They call them embedding models. Okay. So yeah, if you go to models, you will see you can search for, they usually put them under either transformers, right? This allow you to do embeddings. Transformers, you could find task. Well, there's a whole bunch of other tasks here, but look for um, natural language processing. So look for feature extraction. Feature extraction is their own name for for embedding models, basically. And one of them, the one I use a lot, you have sentence transformer. So you see a whole lot of sentence embedding models. So we have sentence transformer, Distilbert, um, all meaning. Yeah, so you have Zenova all meaning, right? You actually have sentence transformer all meaning, LM, which is sentence similarity. Okay, so they classify this under sentence similarity, which is you would use these ones for if you're doing a RAG or something, right? OpenRouter has this as well, so you can go to models, and then there are a whole bunch of them. These are the more modern ones. If you check, you can check embeddings. Yeah, so if you check embeddings, you see embedding models. So embedding models are models that will generate a vector representation of whatever word or sentence or paragraph you give to it. But those ones are for like real life if you want to do really heavy stuff. But for the purpose of classes and training, we have Word2Vec. Word2Vec is basically a shallow neural network that has been trained, so it learns vector representations. Okay. Um, so to get Word2Vec, you use NLTK, use NLTK. So you pip install NLTK and GenSim, right? And then you import NLTK. Then when you import NLTK, you need to also download the Punkt and Punkt tab, right? So apart from Word2Vec, there's also the Glove embeddings. Those are the two that are really used a lot when you want to train models at this level, right? So I'm going to share this, of course. Then, so this is a good example of us doing this, right? So remember, step one is the words. The sentences must be embedded. They must be converted to embedding vectors. So here we have 4 sentences, right? 1, 2, 3, 4. Each sentence, this is a variable length. So for variable length, you always choose a single length and then you can pad. Okay, that's the simplest approach. There are other approaches that I used. So here, the first thing is to do tokenize. So what tokenize is just a very simple function that NLTK provides, right? From NLTK tokenize. What tokenize basically tokenizes the sentence on word boundaries. Simple, easy to understand. So this word, my name is John, is tokenized into this, right? Basically splits into the different words that make it up. And then I also use a lower here to make everything lowercase so that it is stable, right? So for you to now tokenize the entire sentence, you basically take each sentence, right, and you tokenize them with word tokenize. So when you do that, you now have 4 arrays, right? 4 arrays or 4 lists of words. So each list contains the tokenized version. So this is tokenization. We've not done embedding yet. So to now embed, right, with word2vec, you need to first of all train the word2vec model on the words that you have. It's not as if you are training it from scratch or anything, but you're just training it to be able to um, give you good embeddings for this vocabulary. So there's a terminology called vocabulary. Vocabulary refers to the total number of words in your data set that you want to use for training the model, right? So your embedding will be essentially tied to that vocabulary. It's a total number of words, or the total set is a set of words. Words are not repeated. So we will now get the word2vec from gensim.models, right? And we'll now use word2vec. We'll specify all the sentences, right? You can see that these sentences is all the sentences that we've tokenized. Basically 4 sentences, each made up of a list of the words in that sentence. Then we specify the size of the embedding. So here we say we take 100, right? This is not really a power of 2, but whatever, right? So that is the vector size. Then the window 10 is a context window. So think of this as the maximum size, the maximum context, the maximum sequence length, right? That's what context window is. Maximum sequence length. So here we are 1, 2, 3, 4, 5, 6, 7. So we've checked all the words here. There's none that's up to 10. So 10 is a good number, right? But remember, if you are doing this in real life, your context window will have to be much more than that, because if not, you will have a situation where words may not fit or words get cut off. The reason why you need the context window or the window thing is because the word2vec is going to pad, you know, essentially, it's going to pad to make it up, right? So it needs to know whether, you know, what's the maximum length. Mean count, is the minimum repetitions. Workers is basically a calculation thing, right? Sorry, it's a computation thing. The more workers you have, the faster it will do the embedding, right? The faster it will do the embedding, because it's doing in parallel, essentially. SG skip gram, which basically is a number that talked about. I will talk about skip gram later on. Okay, so when you run this, right, you essentially embed, right? So you can then look at the shape of your embedding. You see that we have taken, remember the words here. So we have words here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 20 words altogether, even though there are some repetitions. So the vocabulary will be slightly less than 20 because you don't repeat words in a vocabulary. So if you now look at this, WV will give you the embedding for a single word in this vocabulary. You cannot get the embedding for a word that's not in this vocabulary, right? So this is vector shape. We can actually print out the entire vector and you will see this is the vector now. This is the vector that represents this word film that has been generated by word2vec, right? So you can see it's just a list of floating point numbers, and the number of numbers in this list is 100. That's the embedding depth. So this is how words are represented when you are doing natural language processing. Now, you can then take this and then look for the word that is most similar to another word, right? This other word also still has to be in the vocabulary. If it is not in the vocabulary, we'll not be able to deal with it. In other words, when it comes to word2vec, it's dealing with all the words in your vocabulary, basically all of the words in your data set. So you have to be sure that you have a large enough vocabulary that handles everything. So you can see that here, we now do an embedding. So it's calculating which words are most similar to fantastic. And it gives you the words that are similar and the similarity score, right? Of course, if you look at this, you will see that the one that has the highest score is the word it, which doesn't really make sense. But then that is a glove. The main reason why it is not this good is because the data we have is very small. We just have 5 or 6 sentences, right? And the vocabulary we have is also very small. So you cannot expect high accuracy based on a small amount of data. If you will get much better accuracy if you have many, many, many more words. You actually need, or many, many, many more sentences. You probably need like hundreds of thousands of sentences, right, with word2vec for you to get anything out of it. Okay, so after you have done this, you now have the embed model. So this embed model allows you to pull out embedding of any word. So now, to build what we call the embedding matrix, right? The embedding matrix is just a matrix that holds all the words and their embedding values, right? So you typically will have it in this shape: vocabulary size and embedding dimension. So vocabulary size is basically the total number of words you have in your vocabulary, and the embedding dimension is going to be the size of each embedding, which we had started off by making the embedding dimension here to be 100, right? That's the vector size. Okay, so for us to now build this, right, we can run a simple list, okay? And then we run this thing called index to key. Okay, so what does index to key do from the word2vec? Word2vec will basically generate the index, right, and the key. So for each word, right, it will give you the index, that is the position. Think of it as a position of that word in the vocabulary, right? And then it will give you the word. So that's what we have here, but it starts from zero indexing. So what we have done here is that we have flipped it, right? So the word is now brought in first, right? While the position here is the index, that is the position in that list. But we add +1, so word2vec is going to give you index as zero, you know, zero based, right? But we want to start from 1. So you can see that with this, you now have a word index. So the value of a word index is that I can easily get the number, the location of that word in the vocabulary just by looking up the word. So I know that amazing, for example, is in position 5 in the vocabulary. Absolutely is in position 14 in the vocabulary. And you can see that the full size of this, that's the full size of your vocabulary, is just 20 words that are there. Okay, so that's the word index. Then we now will create the embedding matrix. The embedding matrix, like I say, is a matrix of word index, right? Versus, we've not even gotten to using GPU yet. So word index versus the embedding dimension. Basically, it is the embedding of each word in the vocabulary, right? And that's what we are doing here. So the embedding dimension is to get the vector size. The vector size is going to be 100 in this case because we actually we chose it to be 100. You can just confirm that here, embedding model dot vector size. Remember, that's what we specify when we're creating it. So that's 100. Then the vocabulary size, which is basically the number of words in our vocabulary, right? And the length of the word index plus one. So the reason why we add plus one is that there's something we call padding, which I'll talk about shortly. Padding is just a way to say any word that I do not know, I'll replace it with a padding so that if for some reason you later on want to use this model to do some prediction, and there are some words that are not in the vocabulary, right? You use a padding. It's just saying, yeah, I don't know this word, right? But it should not break your model. Your model should still be able to do something. So the embedding matrix is now made up of um, basically a NumPy array where the number of rows is the number of vocabulary size plus one, right? Where the zeroth element is the um, padding, and then the embedding dimension, that's the depth. Okay, so this will allow you to tune all your embedding. So you now look through all your word index. Remember, your word index allows you to map your word to its position. So you go through the word index. The word index contains all the words in your vocabulary. And the word is W and I is the index. This index also directly maps to the location in the embedding matrix. So you now go and get the embedding of that particular word from your word to vec model, right? And store it in the embedding matrix at the ith location, the location that corresponds to the position of that word in your vocabulary. And that gives you this, and that's the embedding matrix. So embedding matrix is just a saying that all of the words that I have in my vocabulary, I am now giving the equivalent corresponding embedding for it. So the value of this embedding matrix is that it is a lookup table that allows when your neural network is trying to find out what embedding should I use for this particular word, it uses embedding matrix. It's a lookup table. So you give it a vocabulary and or you give a list of numbers that represent the position of a word in the vocabulary because you cannot give a neural network words. You have to give it numbers. So the embedding matrix is a lookup table that it uses. So now let's go to building it. So there's something we call an embedding layer. An embedding layer is essentially a layer that uses this lookup table to generate embeddings, right? Based on position. Simple as that. So we created an embedding layer. And then when you use from pre-train, there are two ways you can have an embedding layer. You can actually train an embedding layer by giving it data, giving it the sentences, the embeddings, and then giving it the meanings, and it will learn, and it will basically learn its own embedding, right? But if you already have pre-existing embeddings that you got, like this one we got from Word to Vec, then you can effectively just use that embedding matrix instead of trying to train your model. But even if you train your model, if you start from an existing one, the model learns faster because it is already smart. It's like you're taking the model that's already smart, knows a little bit about the meanings of words, and then you train it to fine tune and get better on those meanings. So from pre-trained allows you to take an embedding. Remember, this is from our PyTorch, torch.nn, right? So we have an embedding layer. Basically, an embedding layer is, think of it as this lookup table. It implements a lookup table for you, right? Then you get the embedding matrix. So from pre-train, when you use from pre-train, you have to specify the pre-train weights. Essentially, pre-trained embeddings. That's what this is. Okay. Then you also have to specify which dimension or which location, rather, which position this embedding matrix corresponds to the padding index. That is uh, the one that says, I don't know what this word is, right? So use padding. So remember we had the padding index, it was 0. We had shifted everything by 1 when we added 1 here. So the zeroth entry. There's nothing there. So we're using that as our padding. That's what this comment means. So reserve position 0 padding. So specify that same position 0. The padding index is position 0. Right? Freeze is false. Freeze can be true. True means I want this embedding layer to still keep learning, right? I want it to sorry, freeze means freeze the weights. So I don't want it to learn. I don't want it to update the weights. I don't want to change the weights. So this, when you freeze true, it means that that embedding is not going to learn any new information. But freeze false is I want it to learn. So if I'm training this network, this model, it should still be able to learn. So the embedding layer is the first layer that will convert the words into embeddings, right? So after doing that embedding layer, you can now add other things. So this is the complete model where you can see everything comes together. So this model is called a next word predictor, just like what we were doing with CNN and so on. We use the NN.module as the superclass to create this network predictor. In the initial init function, let's look at the several things that are happening here. First of all, we just call the um, superclass as usual. Then we now define the dimensions. So remember, we already created the embedding matrix, which we are passing in here as a property or as a parameter. Okay. So the shape of this embedding matrix, if you pay attention, let me just show you again. The shape of this embedding matrix is going to be vocabulary size by embedding depth, right? So remember that it's going to be vocabulary size. The vocabulary, there are just 20 words, right? There are 20 words. This extra one is for the padding that we put at position 0. The vector size is on, okay? So we get the vocabulary size and embedding dimension. So we now create an embedding from pre-train. This is basically a duplicate of what I've already displayed here. The only difference is here, I'm now putting it inside the model. Okay. So this embedding layer is what will translate whatever words that you have in the vocabulary into the vector embeddings because you have initialized it with the embedding matrix. Then you now have the LSTM. So this time around, we are using LSTM first to train this model. So this model is based on LSTM. And this is a standard LSTM, right? The input side of the LSTM should match the embedding dimension, which is 100. Because what we are saying effectively is that if you want to look at the what we are doing here, we have done a layer. Yeah, so this layer is the embedding layer. And then we now do LSTM. Okay. So we'll talk about the steps later on. But yeah, you have the inputs coming here. And then from here it goes into the LSTM. Then after the LSTM, we now have the linear layer. So remember, the linear layer is always there to do the knowledge representation, basically to store the knowledge, right? Previous layers are more feature engineering layers, but the linear layer always kind of does the knowledge representation. So the input has vocab size. The shape of the input will be the vocabulary size. In this case, it's 21, and the embedding size, right? That's the shape of the input that's coming in. Then the embedding layer. Okay, sorry, let me correct that. The input is actually going to be 21.1. Okay, that's not what I wanted to actually say. Um, so let me back up because the input is actually not that size. The input is going to be batch size. But what I was trying to say is that at this input, you have the embedding layer. The embedding layer, so let's just call it embed layer. So you have the embed layer. And then the embed layer is going to translate whatever comes in. Then you have the LSTM. So that's the architecture we have here. You have the LSTM, and then the LSTM will do the actual sequential passing, learning from the sequence and, making sense of the sequence. Then you have the fully connected layer here. So this fully connected layer is the output that will essentially give you meaning, give the meaning to the what the data that you're giving it to train. Okay, so that's what we are looking at here. So what's happening is I was trying to say something. The embedding layer, right? The input that comes into the embedding layer is going to have a shape of, let's say, batch, right? And sequence length, right? And just batch and sequence length, right? But this sequence length is the sequence is just going to be the position in the position in the vocabulary. The embedding layer will now extend this and give us embedding depth. So we now have still sequence length, but it will now have the embedding depth, right? Which we can just call it dimension or D model or depth. D model is used in the context of transformers anyway. So or attention. So we can just call it embedding dimension, right? That is what will come out from the embedding layer, right? So basically what the embedding layer has done is that it has taken this input, right? And it has extended it from single tokens, right, into the embedding vectors that represent those tokens using the embedding matrix, right? Then the LSTM is designed to have a hidden size of 128. So the LSTM will do its magic and will now give you an output that is the same as the hidden size. So it's still going to be batch size, and then it will be still sequence length if we are taking straight from sequence length. But the other thing we could do is we are taking the hidden internal context. So if we are taking the hidden meaning or the hidden context or the context vector, then this will reduce to just one. But it will now have 128, which is the hidden size of the LSTM. So I hope you understand how the interesting thing with LSTM is that you have choice of whether you want to extract the full sequence length from the output of LSTM or you want to extract just the context vector. But if you're extracting the context vector, then this will just be one. As a matter of fact, I think they swapped the thing. So it's a bit swapped, I think. They actually swap it this way with PyTorch. So the batch becomes second dimension. And I guess that is when you squeeze it, you now have just batch and the hidden size. And then that hidden size now comes into the fully connected layer. You can see that the fully connected layer has 128 as its input, and then the vocabulary size. So the vocabulary size here is 21. What you are trying to do is predict the next word. So if you want to predict the next word, you will predict just the output. Which word is it? But is the neural network or the output, does it know anything about words? No. So what is predicting is not actually the word itself, but the position in the vocabulary that that word should be. And this is a 21 output distribution. So it's not actually exactly going to predict the number. It's just going to give you probability distribution of, oh, this one has the likelihood to be the number that should, sorry, the word that should come next. And that's how, this is how natural language processing is done, right? So you need to know the mechanics behind it, how you handle sequence length, how you handle the meaning of words, you convert them from a vocabulary into an embedding. And then the LSTM does the magic and gives you an intermediate hidden, context, what it thinks the word means, right? And from there, you can use that to predict what should be the next word, right? From the internal representation or the knowledge representation in the fully connected layer. And that comes out as not a single number, but it's basically a classification problem. You're saying in this vocabulary, which of these words is likely going to be the the one that should follow next. Okay, so that's what we are seeing here. Then, so it becomes very easy to just stack all of this up. So the forward, when you're actually running the inference, the first thing is to run it through the embedding. So the X here is going to be an index number, the index number that represents the position of that word, right, in the vocabulary. So that index number is a single integer number. It will get into the embedding. The embedding knows how to interpret it because remember the embedding has a lookup table, the embedding matrix that contains the position versus the actual vector embedding. So the X that you are going to get out from the embedding layer is going to be the vector embedding. It's going to be this, what I just said here, B sequence length embed. Then that output is now passed into the LSTM, right? So when it goes into the LSTM, what you come out with is the LSTM has the option of you choosing the output. This output has the same sequence length, or you can choose to have the hidden state and the cell state, right? So with LSTM, there's some kind of magic that is done where you actually take, when you take this -1, which is the last one, you're actually taking um uh you're taking the basically you're taking this output, right, which corresponds to the embedding dimension, which is this second one. So remember I said it is like 1B 128, that's the ship. So when we take all of this, we are taking this whole one, and then when we take 128, okay, I think it's the other way. What we are taking is output. So let me change that. What we are taking this time is output. So output is always in the shape of uh, the input. The output always has the same shape as the input. It is a hidden and the cell state that of this shape. But since we are taking the output will have the same shape. So it's going to have this same shape as the input. It's going to be the only thing that will change is that this dimension matches a hidden size, but it will have batch and sequence length. So when we use this to extract, we are extracting the whole batch and the whole embed dimension, but we're taking -1 from the sequence length. -1, that means the last in the sequence. So we are basically taking the last in the sequence that the LSTM does, and we put that into the fully connected layer. And so we're going to get batch and 21 output. So that's an explanation of what this does. Now, having done this, right, we can now run it. So the first thing we do is the logits. The logits is basically taking vocabulary size. We'll get some random numbers. So this is kind of, um, trying to show, this is essentially um, just trying to create a random input, right? But since we are taking vocabulary size -1, we are taking all of the possible inputs and probability distribution of the inputs, right? So we have a whole bunch of stuff going on here, but this is kind of probability distribution of input, the words in the input. We are able to get the words because we know the index position of the words in the vocabulary. So this is kind of like generated data. Okay, so that was using Word2Vec. This is using Glove, right? You can do exactly the same thing with Glove, right? So I'm just going to Glove will still do the same thing, right? But you can still do the same thing with Glove. I guess I was trying to show you how you can download Glove. Glove is another embedding approach, right? Another embedding model that you can use for embedding. Okay, so this thing is still not using my GPU. So right. Glow is taking a bit of time, so I think I'll pause it, right? I'll pause it and then I'll continue. So this is now a new set of sentences, the same set of sentences. So to now do inference, right? You would take this set of sentences and then you generate a set of numbers. So the embedding layer, this embedding layer we saw here, is actually going to take the indexes or indices of each word in the vocabulary. So if we go back to where we have vocabulary, you see that the vocabulary, um, let's go, it's a bit way up, right? But the vocabulary has this number. Okay. Maybe I can copy it and paste it down so we will see. But movie is in position 1, ever is in position 2, was is in position 3, and so on and so forth. So that means that if you want to now encode the words for you to use, right? Um, let me paste it here. Let me paste it here in a text block. So yeah, probably should paste it as let me see if I can do this in a faster manner. Okay, so that will show us as a list. Yes. So you will see the numbers here. Now, so if I want to encode this sentence, this movie was fantastic. I love it. The first thing it will do is tokenize it. So it takes each of the words into a separate, into an array of, basically an array of the words. This movie was fantastic. I loved it. Then it will now convert each word into the index in this vocabulary. So this has position 20. That's why we have 20 here. Movie has position 1. So that's why you have 1 here, right? Was has position 19, so you have 19 here. Fantastic has position 18, that's why you have 18 here. I has position 17, so you have 17 here. Loved has position 16, so you have 16. It has position 15, so you have 15. And that's basically how the embeddings for, sorry, the indexes, these are not the embeddings yet, but these are the indexes, right? This forms the input. So the input you normally send into an embedding layer is just an input that contains the indexes of the words, right, in the vocabulary. You convert that into an int tensor because the embedding layer always takes an int because it is going to look up in the embedding matrix. Okay. So these are the same sentences. I was just trying to show here what index is the same thing. So now, if you pass this through an embedding layer, so we already had an embedding layer before. So if you pass it through an embedding layer, you now have a list of numbers where each number represents the full embedding for the first word. So this is the full embedding for the first word, right? And this is the full embedding for the next word. So the whole sentence is going to have a list of embeddings. The whole list of sentences is going to have a list of embeddings. So that becomes a three-dimensional list. So the reason why this now has a size of 1 to 7, um, we have to, so input 1 is just the input of the first one, right? Now, for us to run it, let's just go straight into running it. We now create the model. So remember, we're going to pass the embedding metrics in as well. So we create the model. Now, what I have done is I took the first word, right, which has, the reason why the size is 1 by 7 is there is only one sentence. The sentence has 7 words. That is the first one. This movie was fantastic. I loved it. There are 7 words here, right? 1, 2, 3, 4, 5, 6, 7. So there will be 7 tokens and 7 indices, right? And so we would take this input 1 and we'll pass it into the model. right? We have reshaped it to have the size. It has to have a two-dimensional size. And it does a prediction. And this is a prediction. The prediction, remember, our output is B21. It is a 21 output. So you see 21 outputs here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. This 21 represents the position in the vocabulary. That is the most likely position that matches the next output. Okay, so you can see that this is position 0. This is pad. This is position 1. That represents what was position 1 again? Position 1 is movie. Position 2 is ever. Position 20 is what? Position 21 is um, this, right? And so on and so forth. So each of these represents which word is likely. So what we would then do is to do some kind of turn this into a logistic. So you can see I plotted this output right here. And when I plotted the output, because it is still, I didn't do any kind of logics on this. You see, you have negative values and positive values, right? Now you can do a soft marks on it, and then soft marks will tell you that. So anyway, we take the tokenized sentences. We can now train the model. By the way, this is an untrained model, so it didn't learn anything, right? That's why it's giving negative and positive numbers. Now we take this model and we train. So remember what we say when you're training a model. When you're training a model on a sequence, right? You take the first, you have to take this sequence. From this sequence, we can get 7 um, you know, samples of training data. And the way you get these 7 samples is, if the first word is this, then what should it predict? What is the Y value? The Y value should be movie, because if the first word is this, then it should predict movie. If the first sequence, if the input X is this movie, then it should predict was. If the input is this movie was, then it should predict fantastic, right? If the input was this movie was fantastic, it should predict what? I. If the input is this movie was fantastic, it should predict loved, and so on and so forth. So you would take this and you would generate 6 entries. The first is the one that starts with this. The next one is this movie. The next one is this movie was. That's 3. The fourth one is this movie was fantastic. The fifth one is this movie was fantastic. And the sixth one is this movie was fantastic. I loved. But you cannot use the 7th one, which is the entire sentence, because then you do not know what the Y value should be, what it should predict after it. Unless we want to train it to predict, okay, that is the end of the sentence. So maybe there should be an end of sentence marker. But for now, I trained it on the 6. So this loop does that. Basically, it takes each sentence and it generates that length. So it basically, the length for the entire length of the input, right? You will generate new training X. The training X will be all of the um, you know, sequences up to a particular point, while the Y will be the input at that specific point. So when you look at that, after doing that, you now see that X, when it is 20, which is this, right? The Y should be what? 1, which is movie. When the input X is 21, which is this movie, the Y should be what? 19, which is was. When the input is 2119. So you just see that it's basically taking that sequence and generating, the X values and then generating the Y. And this is just the first X. You could also see that for the entire training X, it gives you the entire list, right? Okay, I only did 1, but okay, I only did training X for input 0, so I only did for the first input. So yeah, there's also left pad. So the next step is to pad the values, because the sequence length is fixed, right? So if you just carry these things and put it, the remaining inputs will have no value. So that's going to be a problem. So what we do is to left pad with zeros. So you can see that that's the next um, um, pre-processing that we do. Remember, all of this is pre-processing words before it goes into the network for training, right? All of this is pre-processing. Okay, so we left pad. So the first one we left padded with 1, 2, 3, 4, 5 zeros. The next one we left pad with 4 zeros. This function, this simple thing does that left padding, and so on. The last one we don't need to left pad because it's exactly the same length, right? And then we take all of this, right? And then the y values, right? We have to make it into a one hot vector. The y values are then converted into a one hot vector, which basically is positional. And that gives you a one hot vector that has, it will have 21 outputs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20, 21, which matches the output we have here. So basically, that gives you your y values. And that's it. So that's just showing you all of that. So we now put all of this together. The training X, you turn the X into a tensor, right? The training Y, you turn it into a one hot. I should have done more with the training X and the training Y because it looks like my training X and training Y was just a single, yeah. So I think I missed that. The training X turns out to be just a single sentence. So the training X should not be a single sentence. It should be all the sentences. So what I will do is I only did it for a range of length of input 0. So I'm going to expand this training X to handle everything. So I'm going to go through all the inputs. So for I in range, for inputs for sentence in input, right? I think that's just it. For item, let me say item, for item in input, right? So input 0 is the item. Here I was just doing only for the first sentence, and I had 4 sentences. So this will now be for all the sentences, right? So if I run this, you can now see I have the same thing for all sentences, right? And the Y's will also correspond. So I basically stack all of them into a single list, right? But they have differing lengths. So that is where that is where this should be just training X0 and training Y0. Well, it doesn't really matter. It's all of it, right? Yeah, so okay. Okay, so the reason why we started with the first one is because this first one ends up you know, it gives us nothing, right? So we shouldn't actually do the first one. So the range should actually start from 1, right? It should start from 1. So we don't do the first one. The first one, we're not doing anything, right? It's from the second I, that's from the second one that we start getting the Y's. So that gives us training X and training Y. Okay, so we don't need this, right? Now we will pad all of them. So for some reason the padding, let's see. Okay. Um, for I in range, length of training X, training XI. Okay, so the okay, so yeah, my uh let's check this. So training X, let's see. There's a bug there. The padding is not padding properly. It's not padding properly. Um, so let's check a few things. Length of training X is 17. Um, there are 17 data samples. Okay. So it's only padding the first one. Um, okay, so it shouldn't be training X minus 1. It should be training X length of uh okay, I think I know the problem. Um, okay, yeah. So the issue is that the formula I was using is using the last one, but I think we should have is using the last one as a length, which is not the correct approach. So what I should have done is while generating this, I should have tracked the longest item. I should have tracked the longest item. So I could track that here with max sequence length, right? And I could say max sequence length equals 0. So since we are doing for I in range 1 to length of item, right? The length of item is actually the sequence length, right? For each one. So we could just say sequence length, sequence length is length of item. Okay, that's the sequence length. So we have 1, 2, 3, 4, 5, 6, 7. Even though the max here is 1, 2, 3, 4, 5, 6. So maybe we can do minus 1, right? As a matter of fact, we could do it this way. Max sequence length is the max of max sequence length and length of item minus 1. So this way we just keep track of the max sequence length. So let me just put that here. So I think that was the piece that I was missing. We should have had a max sequence length. So max sequence length is 6 here. So it's shown here as 6, which is correct. That's 1, 2, 3, 4, 5, 6. So when doing this, I should use the max sequence length here to calculate the padding rather than this. This calculation I did was wrong. I was using the length of the last sequence as a maximum sequence length, but it should have been max sequence length, right? And yeah, so that is what should have happened. Um, okay, So that's something to remember, right? So let's see if this is actually correct. 1, 2, 3, 4, 5, 6. So it passes to 6. 1, 2, 3, 4, 5, 6. So it parts everything correctly. 1, 2, 3, 4, 5, 6. So all of the sequences should be padded to the same length. 1, 2, 3, 5, 6. All right. So we now have that. And then, so this now gives us more information, more data for training. We now create a predictor with this embedding matrix, epochs, learning rate. We use cross entropy loss because this is a classification problem. Funny enough, right? Next word prediction. That's why we call it word prediction. It's like the next word that should come is a classification problem. So we use cross entropy loss. We use Adam because we're using Adam. We use a low learning rate. We could use a higher learning rate though, if we want it to maybe 0.01. We can use 0.01. So let's use 0.01. So we create our model and our parameters. Okay. Then we just review our training X, which is all of this padded, all of them padded to the same um, six numbers, and all of them from this. So remember, this is now the value of the pad, right? That pad index, which we say 0. Pad means this is just a placeholder. Think of it that way. Okay, so to now do the training, it is very simple. We take this input. These are now the input X, and the input Y is a 1 hot. And we just, we have now finished, basically what we have been doing since was pre-processing, encoding, converting the input from a sequence of words to numbers that we now put into a neural network. It's as simple as that. That's what we all did. So you can see that in natural language processing, encoding is a bit more involved. You see, we had to do embedding, we had to do tokenization first, embedding, we had to do a vocabulary, right? And then when we want to now do the training, we convert the words into indexes in the vocabulary, right? And then we convert those indexes. Um, we now generate the training data, which is the first word or the first token and the next one, the first two tokens, the next one, the third one, we generate the XY from that sequence, right? And then we do the padding, the left pad. So those are the 3 or 4 steps. Those are 5 steps that you do when you are pre-processing for natural language to train. But at the end of the day, what we get is still the same as any other neural network. We get is we get a list of data that has fixed length, fixed dimension, basically, fixed size, fixed shape, fixed number of inputs or samples versus fixed width. But here, these are indexes into the embedding matrix. So if I were to pass this through our embedding, let's just try it again one more. I had an embedding layer that I had created just on its own, not part of the network. So this embedding layer, I can still pass this, right? And when I pass this, um, when I pass this, let's see. I want to just show you the shape of what it would look like, right? So we now take instead of input 0, which was just the first one, we will now do an instanceur of the whole input that we have processed. That is training X, right? And then I'll just want to do the shape or the size because this is now a touch tensor. Yeah, it's a function. So let me call the function. So you can now see it has 3 dimensions, like I was saying. By the time you put it into an embedding layer extends it because what is going into the embedding layer, right? This is what we passed in. what we passed in was, yeah, let me put the two of them together. What we passed in was let me call it just input, input tensor, right? In tensor, right? The input tensor, right, is a tensor that you make from training X, right? So the input tensor, right? So we'll now come and print, well, let me call it extensor, extensor. So the extensor is what you pass in. So extensor. So if you look at it, right? Um, yeah, okay, is the size I want everyone to see. So I pass extensor into I pass extensor into this. So you see the size of the extensor is 17.6, which is what goes here, which is the 17 is the batch size, the number of data samples. And the sequence length is 6, which we had padded everything to 6. Then you pass it through embedding layer. Embedding layer will now extend it and give the embedding to it. So embedding layer output will now be batch size, which is still 17 samples. Sequence length is still the same, which is 6. And then the embedding dimension, which is 100 in this case. So that's what will go in, and then we'll use all of that to train this model, right? And hopefully the training should work. We only use 100 epochs, 1,000 epochs, right? And then we can check the losses. You see the losses dropped very fast. We can then now look at a few things, right? We can now try to predict. So the input tensor 0, 5 um, um, is one of those inputs, right? I think this is the first one. The movie, right? Was and all of that, right? So I now pass that tensor back in as an input and I ask it to predict. So you can see it does a much better prediction here, right? There's one that has a very high value, and this one that has a very high value, you see the position. If you count the position, this is position 21, 20, 19, 18, 17. So this is position 17, 21, 20, 19, 18, 17. So if you go and check our this thing again, let's go and check our index again, right? Word index to know which word was at position 17. You see position 17 was what? I. So it is predicting that the next word should be I in that sequence, right? I don't know what we had here, but it's essentially predicting the next word to be the last word, which is interesting, right? But if you now plot it, you will see that at least this time around, you have trained the model. Okay, it says it's loved. So I think I may have loved is, so it predicts it as loved. That's the word that's at that position. I'm surprised. Okay, hold on. Maybe I didn't read it properly. But this is 17, 9 minus 4. Well, so maybe the padding is here. Um, oh, hold on. The padding is not part of the prediction. That's correct. Um, Let me see what I had in my um, in our one hot. Okay, it is part of the prediction. Um, okay, the Y value started from 1 anyway. So the padding, um, the Y values, but if it's a one hot, the one hot is the one hot truly is is let's see. Let me see the shape of the Y. Training Y dot shape. Training Y is still numpy, I assume. Okay. So it's 1721. Okay, so it's 21. I think my graph may have been wrong, but this is telling me that the uh the actual word that is being predicted that has the highest you know probability is loved, which should be correct, right? So that's how you do next word prediction. And we use an LSTM here. The vocabulary was very small. Um, now, the next question is, from here, how do we move from next word prediction to predicting an entire sentence? Yeah, we'll talk about that when we come next week. So when we come next week, we are going to look at large language models and the whole thing, right? So, but in the meantime, you can go try this same example, but use a transformer encoder model instead of an LSTM. Use a transformer encoder. Try to get more a vocabulary that has more words, right? But this is a principle of next word prediction. Now, once you do next word prediction, it becomes very easy to now move to the next, which is what should predicting a whole sentence. Now, the only problem is that there's a difference between next word prediction and generation of the next word. Next word prediction means you are outputting, the output is a probability distribution of the words in the vocabulary. For a small vocabulary, right, that makes sense. But for a large vocabulary, so think of a vocabulary of a million words. Doesn't mean your network output will be 1 million outputs. So in real life, next word prediction is not feasible doing it this way because you're going to generate words. So instead of doing a one hot output, you now do what an embedding, where you have embedding dimension. So it's going to essentially try to predict an embedding, you know, based on what it knows. So that is what we'll talk about next week. That's all from me. Are there any questions?